Hi there, welcome back. We are studying numerical differentiation, and in the previous lecture, we had discussed the 3-point midpoint formula for computing the numerical derivatives and also the 3-point endpoint formula. So, let's take a look at those formulae once again. Here we have the first formula that we see is the 3-point endpoint formula. We see that we want to compute the derivative of the function at x naught, and the values we are using are f of x naught plus h, and f of x naught plus 2h. So these are values on one side of x naught. Of course, we can also consider these values for negative h. So you will have x naught plus h will be on the left side, meaning and then the function value, and then x naught plus 2h is further on the left side, and then you take the function values. So this is what we have for the endpoint formula. Then there is this 3-point midpoint formula, which is invariant under whether h is positive or negative. You flip the sign of h and you immediately see that the sign change gives you there in the numerator as well as in the denominator. So the value remains the same, and the error is of course given in terms of h square. So the error also doesn't change. All right, and we saw this already that both the errors are of the order of h square, whereas the second error is half of the first error. So midpoint formula is better. Okay, so we recall that the initial formula which we had computed using only the x naught and x naught plus h, there the error was of the order of h, whereas here the error is of order h square, and if your h is less than 1, then h square is less than h. So we are going to get a much better error in this case. So if you apply this for our function fx equal to ln x, the natural logarithm, then it's clear that our formulae will give you better answer if you're using the 3-point endpoint or 3-point midpoint formula. So let's go and do it. Here we have the function is ln x, which is ln of x naught, and we also have that x naught is 1.8, h is 0.1. I will not do the whole calculation, but I'll just give you the final answer. The approximation gives you this answer gives you the approximation 0.5545 and then something after that. So if you remember from our previous previous lecture, then this answer correct to 2 decimal points came when the h was 0.01. In fact, this is even better, slightly better than that approximation where we had only used the linear polynomial interpolating your function at x naught and x naught plus h. The endpoint formula already for h equal to 0, 1 is giving you better results. You know, h is 0.1 and h square is going to be 0.01. So it would be still okay if the results were comparable, but already this result is slightly better. Let's go to the midpoint formula for the same f, which is the natural logarithm, same x naught, which is 1.8, and same h, which is 0.1. It gives you this approximation 0.55612817555. This is an approximation on the other side. So if you were to remove this from your actual value, you are going to get a negative value. But in the modulus, the error is better. So this is closer to the actual value of the derivative. Remember, the derivative of natural logarithm is 1 upon x. And so we will have to compute 1 upon 1.8, which we had done in the previous lecture, which was 0.5555555. Continuing. And then we see immediately that 61 is closer to 55 than 45. So this midpoint formula gives you a much better answer. Now we go to the 5-point formulae, and I will not derive them completely, but I will just state the formulae. The derivation can also be done once you use the interpolating polynomial on 5 points. It will be a polynomial of degree at most 4, and then you take the derivatives appropriately and apply the values x equal to xj. So the 5-point midpoint formula, but before we go to the formula, we have to state the assumptions. The assumptions are that there is some interval I and our function is continuously differentiable 5 times, meaning the fifth derivative exists, and that function, the fifth derivative of the function f, that is a continuous function. That is our assumption. And we also assume, of course, that these nodes that we are taking all the while, they lie in capital I. Otherwise, you cannot apply the function f on these points. So midpoint formula, you see, is very simple. It doesn't have the f of x naught term. It has a f of x naught minus 2h, f of x naught minus h, f of x naught plus h, and f of x naught plus 2h. Those are the 4 values that we use with the coefficients 1, minus 8, 8, minus 1. And we divide the whole thing by 1 upon 12h. And the error formula is h power 4 upon 30, the fifth derivative of the function f, evaluated on some xi, which is between x naught minus 2h and x naught plus 2h. Okay, this is the midpoint formula, and we also have the endpoint formula, which starts from x naught and then goes to x naught plus h, x naught plus 2h, x naught plus 3h, x naught plus 4h. But it doesn't have to be positive, it could also be on the negative side. And the coefficients are slightly on the higher side, 25, minus 25, 48, minus 36, 16, and minus 3. And you can put h to be positive or negative number. This is why we only say that xi lies between x naught and x naught plus 4h. We are not saying that it's in the interval x naught comma x naught plus 4h, because if x naught happens to be bigger than x naught plus 4h, then the interval x naught comma x naught plus 4h will be empty. So the only way to state this precise is that there is a xi which is between these two numbers. We don't say which number is bigger, which number is smaller. Okay, so as expected, here the error is to the fourth order, and so in fact, if you apply the same this formula to the example natural logarithm of x for x equal to 1.8 and h is 0.1, then the error will be of the order of 0.0001. Okay, it is 1 upon 10, and the error will be the fourth power of this of that order, and so it's going to be the square of 0.001, and so it's going to be 0.00001. Okay, we will not do those examples here, but let's discuss this midpoint vis-a-vis endpoint formulae. You know, it may seem that the midpoint formulae are much better because they are simpler to operate than the endpoint formulae. First of all, you have fewer number of function values to compute, and the coefficients are also smaller, and you are in the end dividing by 1 upon 12h, which is same for midpoint formula and the endpoint formula, and the same thing happened even for the 3-point formula. So these numbers in the denominators are not changing. We are also getting the errors to be much better. For the midpoint formula, it is h power 4 upon 30, which is smaller than the error in the endpoint formula. This is called the truncation error. So this truncation error is h power 4 upon 5 for the endpoint formula, whereas it is 1 by 6 of that in the midpoint formula. So the errors are better. The formulae are simpler to operate. However, what may happen sometime is that the point x naught on which you want to compute this approximate derivative may be towards the end of one of these intervals, one of these endpoints of the interval. That may happen, and therefore all the nodes that you need to compute the midpoint formulae, they may not lie in the interval hi. So what may happen is that your interval may simply be 1, 2, and you want to compute this derivative at some point which is very close to 1. That may happen. So in that case, instead of taking your h to be very small, you can of course take h very small, right? Then even if your point is close to the endpoint, it is not exactly equal to the endpoint. So there are there are infinitely many points, uncountably many points between your point x naught and say the leftmost endpoint of the interval, say a. So a minus x naught is non-zero, therefore you can break it into any number of intervals that you want, but then that will force you to take h very small, and we don't want to do that. We will explain this later in the same lecture, today's lecture itself, but that is something that we don't want to do. We don't want to take h very small. Therefore, we will then look at the other side of x naught, and we will take the endpoint formulae by looking at the behavior of the function on the other side of the point. Of course, and we also notice that the endpoint formula is valid for negative h. So if your x naught is very close to b, you will take x naught minus something, x naught minus twice something, x naught minus thrice something, x naught minus 4 times something. So we will be taking the endpoint formula, but on the negative side of x naught. We will be able to do of these things. And as I have remarked this several times, the midpoint formula stays the same, whether you take h to be a positive quantity or you take the negative quantity of the same magnitude. The midpoint formula will give you the same number. Okay, so we have seen several methods to compute numerical differentiation f prime at x naught, and before we go on to numerical integration, what next can you do? Is there anything further that one can do? And of course, you can compute higher derivatives. You can compute double derivatives of your function at x naught. You can go even higher. You can go to third derivatives, fourth derivatives, and all those things. Just to give you a test of these formulae, I will give you a formula, but we will not really derive this in much detail. This formula is written in the following way. Now you notice that the denominator has become h square. In the 3-point midpoint formula or the 5-point midpoint formula, we had noticed that we had 1 upon 2h or 1 upon 12h. Okay, so there we did not have square of h, but now we have square of h, and that is indeed there because we are taking the second derivative. If you write down the formula for the first derivative, there will be an h in the denominator. It will be f of x naught minus h minus f of x naught upon h. Then this is your first derivative. Second derivative will be f prime of x naught plus h minus f prime x naught, whole thing divided by h. And in the f prime x naught plus h and f prime x naught, their approximate formulae give you an h in the denominator already. So that will come down further and give you an h square. Okay, so those are the h square that we get, but rest of the things stay essentially the same. And here our error is in the fourth derivative of the function evaluated on some xi, where xi is between x naught minus h and x naught plus h, and you would have guessed it already that this is the midpoint formula. You can similarly derive the endpoint formula for this side or that side. So this is the 3-point midpoint formula. There is a 3-point endpoint formula for a double derivative, and similarly the 5-point formula. Okay, now the time has come to discuss one of our old friends, a very old friend and also a nemesis, the round off error. So there is an error that happens. Of course, there is the truncation error, which we already know, which is given by the error coming from the interpolation polynomial, which was of the order of h in the initial case, then h square for the 3-point formulae, and of the order of h power 4 in the 5-point formulae. But there is also the round off error. So what does it mean? So let's consider our 3-point midpoint formula once again, which reads as it is given here. Now we are going to compute various these values. So this f of x naught plus h, that is going to be computed. F of x naught minus h is also going to be computed, and in these computations we will encounter some rounding of errors, because although typically the expressions will be infinite decimal numbers given by decimal representations with infinitely many digits, we are going to use only finitely many of them. So there will be round off errors. So suppose for f of x naught plus h, the error is e x naught plus h. And for f of x naught minus h, suppose it is e x naught minus h. These are the two errors that we have. And so we will actually be using the numbers f tilde x naught plus h and f tilde x naught minus h. We will not really be using the infinite numbers, the numbers which are given by infinite decimal representations, which are the true values of the function at x naught plus h and x naught minus h, but we will be using these f tildes. Okay, so there is already an error there. So what is the error? The f values are f tilde values plus the round off error. This is by definition, right? So f minus f tilde is our round off error. So f equal to f tilde plus the round off error. Now we put these values back in the midpoint formula to compute the total error. The total error will be given by the rounding off error in this highlighted formula. We will have to divide by 2h also, minus the truncation error which we have here already, the h square by 6, the third derivative of f at xi naught. These together give you the total error. Okay, so you have e x naught plus h minus e x naught minus h. It will come with minus sign because our highlighted formula tells you that the x naught minus h function value is coming with minus sign. So this is e x naught plus h minus e x naught minus h, whole thing divided by 2h, which was the 2h coming from our formula already, minus the truncation error. This is the whole error that we will be working with. We need to give some estimate for this. So suppose the rounding of error, they are bounded by some number epsilon positive. Okay, and suppose also that the third derivative, we have assumed that our function is 3 times continuously differentiable for the 3-point midpoint formulae or 3-point endpoint formula. So our f cube will be continuous on that interval, and therefore there will be a maximum attained by f, the third derivative of f. Let's call that maximum to be capital M. Then this total error is less than or equal to epsilon by h. So here what we have is that we have basically two expressions in the modulus, and we are actually taking the difference of those two expressions. The mod of a minus b is less than or equal to mod a plus mod b. So these two expressions are less than or equal to modulus of the round off error plus the modulus of the truncation error. Okay. Now in the modulus of the round off error, you have the lower side is mod of h, the denominator is mod of h. Here we are assuming the h to be positive, so that 2h comes out right away, and the numerator is the e x naught plus h minus e x naught minus h, but inside a mod. And once again we use the formula that mod a minus b is less than or equal to mod a plus mod b. So this numerator of the round off error is also less than or equal to mod of e x naught plus h plus mod e x naught minus h, which are both less than epsilon. So the numerator is less than or equal to 2 times epsilon. And you have denominator 2h, the 2 get cancelled, and that's why we get epsilon upon h here. And the truncation error, because the third derivative is bounded above by m, you simply get h square by 6 capital M. This is the total error. This is the upper bound for the total error. And if you wanted to reduce the truncation error, which is h square m upon 6, you will have to reduce h. But the problem comes that when you reduce h, the round off error, which is epsilon by h, that will grow. So that's the problem. So if you cannot reduce h too much, because then the round off error becomes huge, so you have to find an equilibrium. You have to find some golden mean somewhere to take a decision. So in practice, therefore, it is seldom advisable. It is seldom advantageous to let h be too small, because then the round off error will dominate the calculations. Although here we are lucky for 3-point formula because it is only epsilon by h. If you are computing the higher order derivatives, then the powers of h will increase. And then again, the round off errors will become too large. So let's do this by an example. So suppose we consider these values of the sine function. We consider these values for 0.8 to 0.899. And you see that the distances from these nodes from 0.9 are decreasing, and then we take the other side of 0.9, so you will have 0.901, which is symmetric to 0.899. Then you have 0.902, which is symmetric to 0.892, all the way up to the node 1.000, which is symmetric to 0.8000. So these are the actual values of the sine function, and we will approximate the derivative at 0.9000, where our function is sine x, and we will be using this formula, the very first initial formula which we have studied, f of something plus h minus f of something minus h upon 2h. So sorry, this is the midpoint formula that we are using for 3-point for different values of h. And the values of h will go from 0.001, because we have here 0.901 and we also have 0.899. So from 0.001 to 0.01 to 0.1. Those are the values of h that we are going to take, and here are the results. So if you take 0.001, the derivative approximation is 0.62500 and the error is 0.00339. We are increasing h and actually the error is decreasing. We increase error for h further and the h error has further decreased at 0.010, which is 10 times the original h we started with. The error has gone down by quite a considerable margin. By error, I mean the magnitude of the error, although there is a negative sign that has come there. For 0.020, the error seems to stay the same. But of course, remember that we are only using the first 5 digits. We may be rounding or chopping. At 0.05, also the error has now grown in magnitude, but it is still better than the error at 0.005. Right here, you had 0.00039, whereas in the magnitude, this is simply 0.00021. If you were to use the rounding thing for 4 digits for error, the error for this 0.005 will be 0.0004, whereas this is 0.0002. Then at 0.1, the error has really grown much. In fact, here between 0.05 and 0.1, we have not taken too many nodes. If you take many nodes, then you will also see that the errors are not growing too much, but they are also growing slightly in a slower way. So the errors are, of course, for error we have to know the actual value, and the actual value is this cos of 0.9, which is 0.62161, and the optimal choice seems to appear between these two values. So these are really our optimal values. Right. Really it is between 0.01 and 0.02, but if optimal values otherwise are between 0.005 and 0.05. So let's see what the error actually looks like. So this is the error, epsilon upon h plus h square by 6 into m. This is the upper bound for the error. We want to see where the upper bound is taking the minimum value depending on the values of h. You will use calculus because it's a function for calculus for h, a differentiable function. You are not taking the h value to be 0, positive values of h. and using calculus you will see that the minimum value of this error appears at this particular number, 3 epsilon by m cube root. So epsilon, remember, is the upper bound for the rounding of error, and capital M is the maximum or the upper bound for the third derivative of your function. So for our example, we can compute both epsilon and capital M explicitly. The capital M, first of all, which is the maximum of the third derivative on the interval 0.8 to 1, because we are going from 0.8 to 1. 0.9 is really in the middle of this, and we are applying various values of h. So this is maximum of mod cos x and 0.128 to 1, which is going to be cos of 0.8. We know that cos value decreases as you go from 0 to pi by 2. And the cos of 0.8, once again, we use approximation that this is 0.69671. The values of f, we are taking only the 5-point decimal values. So the round off error is 5 into 10 power minus 6. Okay. And then you compute h, which is 3 times epsilon. This is the round off error epsilon. This is the capital M. And indeed, we see that the optimal value is 0.027. This is somewhere between 0.005 and 0.05. This is really the optimal value of h. So in some explicit examples, we can compute the optimal value of the h that we need to get the best approximation. It's not going to be possible to compute this optimal h because you will need the knowledge of the third derivative. Here we were lucky to have the information on the third derivative, so we could compute the optimal value. But in general, it will not be possible to compute this optimal value. So what we should be aware of is that reducing the step size is not going to always improve the approximation. You are not always going to get better and better approximation by blindly choosing smaller and smaller values of h. That is the lesson that we must take from this. This is why I told you in that we are not going to apply the midpoint formula by reducing the size of h if you are closer to one of the endpoints. This is particularly the reason that we cannot blindly reduce the size of h. So if your x naught in the derivative formula happens to be closer to one of the endpoints, then we will instead use the endpoint formula where you are going to look at the behavior only on one side of x naught rather than reducing the size of h. So here we have considered the round off error problems for the 3-point formula, but similar difficulties are there with all the differentiation formulae and more so for the higher order formulae. The reason is that we will have to divide by a power of h. That's basically the reason. And this is what is called instability. So we understand this very well when we discussed machine arithmetic in the beginning. We understand that division by small numbers will tend to exaggerate our error, and therefore this operation will have to be avoided as much as possible. But it's not always possible. You cannot avoid the problem entirely, although the higher order methods, so I'm not talking about the higher order differentiation, but the higher order by putting in more points, that will typically reduce the difficulty. Because what happens is that your truncation errors, they become small, and therefore with the same size of h, your truncation errors are almost negligible. So you don't have to reduce the step size h too much if you are using the interpolation formulae, interpolating polynomials for more number of points. But then of course you have to then compute a higher number of function values, so you will have to see. And this is why I said that the 3-point formulae and the 5-point formulae, these are the most common. One doesn't go beyond 5 because then there will be too many formulae function values which you will have to compute, and again there is a possibility that the round off errors will get bigger and bigger. So as an approximation method, the numerical differentiation is the unstable method. So there are these numerical methods which are stable methods, and then there are numerical methods which are unstable. What it means to say is that small values are needed to reduce the truncation errors, but these small values will also cause the round off error to grow. These are what are called unstable numerical methods. This is the first particular example of unstable methods that we have encountered. We are likely to encounter many more, and if it were possible, in the best possible scenarios, in the ideal world, we would not use these methods, but these are very much important. Numerical differentiation is important. That's why we are doing it before numerical integration. So for instance, other than being used for computational purposes, these formulae for computing numerical differentiations are going to be used in the ODEs and PDEs, getting the numerical solutions for the ordinary and the partial differentiation equations, differential equations. So this is where we end our lecture today. We are done with numerical differentiation. In the next lecture onwards, we are going to study numerical integration. So that's the more and more interesting part which is coming up. So hope to see you then. Thank you.